One application of the dot product is in physics. So in physics, a very simple approach to work is taught. Work is often taught as being the scalar that you get from multiplying a force and a distance. And the simplistic, not simplistic, but the simple idea is that force and distance are first often taught as scalars. So force, the number, times distance, the number. How far did the thing travel? Force is in newtons, I think, right? And distance is whatever, meters. And then when you multiply a number and a number, you get a number, and that work is it in joules? I think that's the correct unit anyway. This is only true though for movement that happens on a straight line. But the issue is that work happens with motion not occurring on a straight line. And so, more generally, you can actually view force the way it really ought to be viewed, which is a vector. A vector, right? So you push something. Informally, I believe a force is a push. Please don't tell the physics professors that I'm trying to talk my way through physics. And then the distance should really be replaced with a slightly more general concept of displacement, meaning the idea so the force vector is sort of like when you push an object and it's the you intend an object to go a certain way. The displacement vector is more like where did that object truly end up, right? And so when you dot the two vectors together, you get a scalar, and that scalar is truly what work is. This is sort of the idea it's getting at is instead of in a straight line where all the force that's applied, if the object can only move in the direction that you push it, the dot product here, it's really what it's trying to do is kind of it helps, I guess you could say, scrape away the lost. I don't want to say force or work, but the work that's actually done, it's this dot product is really, I guess, accounting for the fact that sometimes the object moves not in the same direction as the force. So you maybe have an object like moving in space where there's very little gravity and it's moving essentially in a straight line, and then a rock hits some object in space, and the when a rock hits that object that's moving, the object doesn't automatically move in the direction that the rock had collided with it. Now the original object probably moves in some new direction. Okay, there's a second application of dot product. I'm just going to kind of go through this slide and say maybe take some notes, but I used to teach this topic more thoroughly in Calc 3 and then realized we don't use it in Calc 3. So hold on to these formulas. You might need them in a future class, especially in some areas of math and perhaps in physics, but they're just formulas and they're kind of painful to memorize. So I thought look at some pictures in the book, and there's this a concept of projecting one vector onto another. Basically, the idea is if you have a vector called b and a vector called a, and they're both given to you, I like to think of it as if vector a is drawn on the ground and vector b is maybe, let's just say, pointing above the ground. Like it's maybe the vector b starts at the same place as vector a, so a point on the ground, but vector b I just tend to visualize as ending above the ground somewhere. So the arrow is kind of pointing upward, and then the projection is about where does the sun need to be located. So high noon, at some point, the sun is located directly above where the vector b ends, and then casts a shadow onto the ground. And in fact, if it's aligned all correctly, the vector b casts a shadow directly onto vector a. And the length of that shadow is computed using a dot product based formula. And then using that, you can create a vector that is pointing in the same direction as vector A, and its length is that shadow, basically. That's called the projection vector. So there are several formulas. I presented them here. There are several different ways to present some of these formulas. It turns into a lot of things to memorize, I guess. But I think this is truly a topic that you just look up the formula need when you need it. But since it was an application of dot product, I thought I'd just present it this way. So for this class, really don't worry about it. I don't think we're going to need it. I did try to leaf through the entirety of the portions of the book we are covering this semester, and I don't think it's going to be necessary, but if that's kind of an oopsie, we'll just come back to it when we need it. Okay, that really kind of ends the topic of the day, but it will be helpful as a preview to talk about determinants for the next day's class material. And you need this thing called a determinant. It's just an unfortunate thing that if you have taken linear algebra, you already know how to compute this, and if you haven't taken linear algebra, maybe you haven't seen this. It's not too bad of a computation, so let's just go through. So writing a matrix like this, a matrix itself should be written in square brackets, or in some books using round parentheses. I have an example of a 2 by 2 matrix here. In this class, we only ever deal with square matrices. And if I instead switch the square brackets to be vertical bars alone, that's going to be the determinant. Okay, so the determinant is the determinant of a matrix is going to be a number or a scalar. And in the case of a 2 by 2, it's going to be opposite corners times opposite corners, and you subtract. And the order, of course, of subtraction is going to matter. So it's upper left times lower right. And then you subtract the off-diagonal elements, or along the counter-diagonal, b times c. So here's an example. Determinant of the matrix where the first row is 1, 2, and the second row is 3, 4, gives you the scalar -2. Here's another example. First row, the matrix is 3, 4. Second row is 2, 10. But because it's not just the square brackets would say, hey, house these 4 numbers. Make sure these 4 numbers live in the shape of this rectangle. That's all a matrix is. You know, a matrix is very much like a vector, in that a vector was just numbers stored in angle brackets. Here we're just storing numbers in the shape of a rectangle. That's all a matrix is. And then if we instead, though, have the vertical lines, we mean to actually go through this determinant computation process, and here we're going to get 22. Here's another example where all I did was I took the upper right corner of 4 and switched that entry to be a -4 instead. And so you have 3 times 10 minus now -4 times 2, and that should end up giving you 30 plus 8. Okay, 3 by 3 determinants are a little more work, and so by example, I'd like to show you what needs to happen. So let me start talking through the example here. We've got this 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and the vertical bars mean we need to we're going to compute that 3 by 3 determinant, and it is computed in terms of 2 by 2 determinants. So first of all, there's many ways to do it, but at least the way we're showing on the slide is that the entries of the first row will be the coefficients. So you see 1, 2, 3 shown here as 1, 2, and 3. And then you actually alternate for these numbers plus, minus, plus. So there's a plus in front of the 1, a minus in front of the 2, a plus in front of the 3. Don't ask why, it's just kind of how it goes. And then what we're going to do is create 3 separate 2 by 2 determinants. So first of all, what you do for this first one is you hide the first row. You always hide the first row, but you hide the first row and then you hide the first column, and you're left with 5, 6, 8, 9, which are thrown here. And then now you hide the first row, so just kind of visually hide where this one, just cover the 1, 2, 3 with your arm or your hand or with a pencil, and then now hide the second column, hide this 2, 8, and 5. Sorry, 2, 5, and 8 with a pencil vertically, and then the numbers you'd be left seeing are 4 and 6 for a row, and then 7 and 9 for another row. And so that becomes the numbers for another 2 by 2 determinant. And then last, still hide the first row, but now hide the third column, and you have 4, 5, 7, 8. Okay, we're not quite done. Now we just need to do the computation. I appealed to the 2 by 2 determinants we had computed, and here they are. I didn't even bother simplifying. Right, so 5 times 9 minus 6 times 8, and then over here 4 times 9 minus 6 times 7, and then over here 4 times 8 minus 5 times 7. So there it is. This is now a scalar. I just didn't feel like simplifying any further. Here's another example, just to make sure. So the entries of the first row will become the coefficients. So 3, 0, 1 are written here, here, and there. We are going to again alternate plus, minus, plus. So there's a plus in front of the 3, a minus in front of the 0, and then a plus in front of the 1. And then we will always hide the first row, but then to fill in the first 2 by 2 determinant, we're going to hide the first column, and then for the next one we'll hide the second column, and for the last one we hide the third column. And then if we go ahead and do the computations of the three individual 2 by 2 determinants, you get an expression that looks like this. Okay, technically it is a minus sign in front of the zero, just from this idea of this alternating plus minus plus. But, well, because it's going to be 0 times whatever, it's actually not going to matter, right? So in this case it drops out, but technically it is a minus in front of the zero. Had we not had a zero here, right? If this had been a different number, like a 28 or a -5 or whatever, you still need a minus sign. So let's say this number 0 instead had been a -5, then it'd be a minus -5 here instead.